All right, any questions about the test? Again, since you can use your notes on that, I don't worry too much about timing-wise. All right, so let's get started in material. I just wanted to mention this from last time that I forgot to mention before we left. So we dealt with linear functions in our work problems in 2.3. That's what we were doing last time. Obviously, we went over pretty much all those examples. In section 2.3, all of our math modeling, all of our applications were with linear equations. Later on in the course, we'll do math modeling and applications with other types of equations, like quadratic equations, exponential equations, logarithmic equations, and functions like that. So this one is all linear stuff. If I ask you anything from section 2.3, it'll be linear. Okay. That's it. So now we're going to get into section 2.4. And 2.4 is on linear functions from data. Obviously, in 2.3, when we were creating these linear functions, sometimes we had 2 data points and we created a line. But we created the line with the use of algebra. We said, oh, the 2 points are points on the line, so let's create the line. Or we created a line based on what we knew about the slope and the y-intercept. And so we were just using algebraic, the same types of algebraic techniques we used in 2.1 and 2.2. Okay. Now what we're going to do is we're going to use some collected data. We're going to collect data on 2 variables. One we'll call x, the other we'll call y. Traditionally, you can technically use any letters you want. So you could look at that didn't work. Some data. So the next slide, I'm going to show you some data, and it comes from this information. It's about oil consumption per year. Okay, so here's some data on oil consumption per year. In the year 2009, the world oil consumption in billions of barrels of oil was 31.42. So 31.42 billions of barrels of oil. And you can see that consumption each year from 2009 through 2015. What we're going to do with those data is that we're going to create a scatter plot. In other words, I'm going to take the Cartesian coordinate plane and I'm going to create a point on the Cartesian coordinate plane for each one of these pairs. Now we can do that in a couple of different ways. We'll see a couple of different ways we can do that. But it's basically like having the x value of 2009 and the y value of 31.42. That'll create a point on the Cartesian coordinate plane, and I'll just create that point. And then I'll do the same thing for 2010 and 32.43. and 2011, 32.72. And that's what it looks like when I do that. When I set up an X and a Y axis, and I label my X axis 2008, 2009, and so on and so forth, and then my Y axis will start at 31 and end at 35.5. When you plot each of these points, it looks like this. Now, we're looking for a pattern in this data. And what we're going to do is we're going to ask some sort of technology for a regression line. A regression line is the line that best fits the data. In mathematics, we also call that a least squares regression line. I'll talk about what the least squares is referring to in a little bit. But it's the line that best fits the data. Now, no line is going to perfectly fit the data, because if I take any 2 points, let's say I take the point whose x value is 2009 and the x value is 2011. If I go through those two, we're going to be a little bit off on the 2010, right? And if I did 2009 and 2010 and I created that line, we're going to be a little bit off on 2011. So our goal is to create a line that best fits the data so that we're off by as little as possible on as many points as possible. And that's the least squares regression line. Along with that least squares regression line, technology is also going to give us a correlation coefficient. When we are creating a linear regression scenario, the correlation coefficient is called a Pearson correlation coefficient. Pearson is just the last name of some mathematician. And it's labeled as R. The value for the Pearson correlation coefficient will always be between -1 and 1. The closer it is to 1, the stronger our positive linear relationship is. Let me rephrase that. The closer that R is to 1 means these points are really close to being a straight line with positive slope. If we have a correlation coefficient which is really close to -1, then these points are going to be in a straight line or close to a straight line with a negative slope. And if the correlation coefficient is closer to 0, then the points aren't going to look like a straight line. They're going to look really messy and scattered, and there'll be no patterns in it. So 1 means they look like a straight line. Close to -1 means they look like a straight line just with negative slope. Close to 0 means they don't look like a straight line. Here's some examples with lots of points so that you can kind of see what's going on. So in this top line, when all of our points like form a perfectly straight line, then we get an R value of 1. If there's kind of a pattern that goes up and to the right, then our R value is, in this case, 0.8. You can see that when you get to 0.4 or 0.0 or negative 0.4, they look to be just a bunch of points scattered about. The negative 0.8 is basically just negative slope on that line. The negative 1 is just negative slope on that line. If we looked at our example, the oil consumption, this looks fairly straight, like a straight line. It's not a perfectly straight line, so it won't be exactly 1, but we would expect a positive R, which is fairly close to 1. Because it looks pretty much like a straight line, not perfect, and it has positive slope, generally speaking. By the way, any positive slope gives you an R value of 1. So whether it's a very steep positive slope or just a gradual positive slope, that's all R value of 1. Negative slopes, all R value of negatives or negative 1, no matter how steep it is. Now, one other thing that we always mention is that when we're creating the least squares regression line and getting the Pearson correlation coefficient, this is determining a linear pattern. There's obviously lots of patterns that are not linear. Like in this one, it looks like a W. This first one on the lower left looks like a W. There's a pattern there, but it's not linear. So it's also going to have a correlation coefficient of 0 if I try to fit a line to that data. Over here at the bottom right, we have a circle. There's a pattern there, but no straight line is going to fit that very well. So Pearson correlation is picking up how linear of a pattern it is, not just if it's pattern. There's other patterns out there that this will not pick up. For this class, we're going to use a cutoff value of 0.75 to determine whether it's a strong linear relationship or not a good linear relationship. Any R value, which is under 0.75 in absolute value, we're going to say it is not a good relationship. Any R value that's bigger than or equal to 0.75 in absolute value, we're going to say is a good relationship. You have to draw the line somewhere between good and bad. Okay. For this class, we'll use 0.75 as the cutoff value between a good and a bad relationship. Strong relationship means that the line will fit my data well. Bad relationship means that my line does not fit my data well. Now we're using 0.75. Other classes, like if you go into psychology class or sociology class and they're doing correlation, they might use a much lower R value as their cutoff between good and bad. Okay. We're using 0.75 because for one, we're going to use pretty small data sets. And with small data sets, yeah, we don't get like general patterns very well. So we're going to use pretty small data sets. And also, we want there to be a very fairly clear relationship. We don't want things that look like, you know, that 0.4 to highlight a relationship. But in certain realms, they do. In certain realms, they're just looking for some sort of a pattern. And that's especially the case when you get into like social sciences. Like any R, but they use really small R values there as they're cut off between significant and non-significant. Because a lot of times they're dealing with really large data sets, and also they're just looking for any slight pattern, okay, or any significant indicator. Now, here's where it comes down to. How are we going to get this line? Well, in this class, you're going to be given the line. Okay? On all of the homework assignments, on all of the tests, you're going to be given this line. In reality, you go into Excel or you go into your calculator and you ask your calculator to give you the line. So, in the example I had with oil consumption, when I put those data in, I got the line y equals 0.5611x minus 1095.6. And when you do that, usually you get an R squared. R squared is just the square of R, right? And depending on what technology you have, it'll give you both the R squared and the R, or maybe just one of the or the other. Okay. So the R, the Pearson Correlation coefficient, was 0.9923. The R squared is just 0.9923 squared, which is 0.9847. Obviously, we're judging the good fit or bad fit based on lowercase r, Pearson correlation coefficient. That's bigger than 0.75 in absolute value. And so this line, we would say, fits our data well. Okay. So going back here, that's what we would get. We have a little bit of time, so let me show you how you would do that in Excel real quick. You don't have to do this, but what would happen is, I gotta get up to Excel. So I'll put year as the X values, and then I'll put in all those X values, 2009, 2010, 2011, 2012, 2013, 2014, 2015. I think that was it. Yep. And then I'll put in the corresponding oil consumption in billions of barrels. So that was 31.42, 32.43, 32.72, 33.22, 3.73, 34. I think I got all those right. Let me make these slightly bigger. So there we go. So there's the year in the oil consumption. And all I have to do, there's actually two ways to do this. I'll do the easy way. I'll insert a scatter plot. There it is. Looks familiar. And then I'll ask Excel to put a trend line on this. Now, the way I'm going to do it is I'm going to go more options. I'm going to put a linear trend line on it. And then I'll display the equation and display the R value. Technically, when I display the R value, it always displays the R squared. So I'd have to take a square root of that number to figure out what the R value is. And there you go. That's what we have. That's exactly the same numerical values we ended up with. You can also have a TID4 calculator do the same thing using linear regression in the TID4 calculator. You have to put the data into your stats lists and then have it generate out a line. Okay. There is another way. I forgot how now. So you can also look up formulas. Where's the regression? Uh-oh. Did I miss it? There is a linear regression in here. I just forget the typing in of it, though. I don't think it's linear estimation. Known Y's. X's. Is that it? There we go. Linear EST, not I was thinking LINRAG. But here's what we get. We get 0.5611. That goes out more decimal places. That gives you the coefficient of the X. And then the negative 1096. That's giving me the, again, it's cutting me off however many rounding spots based on how big the thing is. But that also gives me my line if I want to. And then another one, you can also find the Pearson correlation coefficient. By just typing in your X values, comma, your Y values, or vice versa. It turns out Pearson correlation coefficient doesn't matter. And so that's your R value, 0.9923. Okay. So there's ways to do this in Excel. That's the only point I'm making. And it's pretty straightforward, it's just a few buttons. Okay, I'm not gonna have you do that on any homework assignment. I will give you the lines. There's also ways you can do that with your TI-84 calculator. Again, I'm not gonna ask you to do it with the TI-84 calculator. If you want to, it's just in the stat menu under linear regressions. Okay. Stats, tests, linear regression. But there you go. So we get the regression lines from technology. And once we do that, we're going to answer some basic questions. We always are going to ask, is this a good fit? And yes, this one is a good fit. This line fits the data well. And then once I know what the regression line is, I can do predictions. This one says, what would this line predict the oil consumption to be in 2018? And all we're doing there is saying I'm given a line. I just need to understand what that line means. X is the year, and Y is oil consumption in billions of barrels of oil. So if I plug in 2018 in for my X, I can figure out the oil consumption or at least the approximate oil consumption. That would be in billions of barrels of oil. And so I'll round this to 2 decimal places because all of our oil consumption was. That would be 36.70. And that would be the oil consumption in billions of barrels of oil. So this would predict that in 2018, there would be about 36.70 billions of barrels of oil consumed worldwide. That makes sense? Once you have technology give you this, or once you've provided this via technology, then it's basically just like a word problem where we've already been given the equation. Okay. And that's what makes 2-4 pretty straightforward. It's basically, once you get that equation, then it's a word problem with a given equation. And that equation comes from technology. There's a lot of stuff embedded in that technology. There's actually, you can actually do it by hand if you want, but it's really cumbersome and time consuming. Okay. So we'll just provide that on a test because you won't have access to Excel and we don't need to take the time to learn how to do that on a calculator. If you want to do that, that's more of a stats problem to actually create the line. So let's look at a second example. What we're going to start with is some data from Brady scorecard points and murder rates for 2 different years. I use this example in stats as well, if you've seen it. Brady scorecard points are such that each state gets a scorecard and The higher the number, the stricter the gun laws. Okay. So Wyoming has less strict gun laws than Michigan. Maryland has more strict gun laws than Michigan. And if you plot the scorecard points out compared to the murder rates, you would get a scatter plot that looks like this. So scorecard points are my x-axis, murder rates are my y-axis. Now, this is not nearly as good of a fit as our last example, right? Our last example was much more linear. But we still have a general pattern of moving up and to the right with these points. So our general pattern is moving up and to the right. If we had Excel or our calculator give us the least squares regression line and the Pearson correlation coefficient, it turns out in this example, we would end up with y is equal to 0.07x plus 4.65 with an R value of 0.7723. It's 0.7723 as an R value, indicating that our line fits the data well or fits the data poorly. Well, in this class, it's above 0.75 in absolute value. So we have a good fit. Since the R value is at or above 0.75. But obviously this was a lot worse fit than our last example. Our last example was like R value 0.99, right? So 9923 or something. That was a better fit. That was closer to 1. Closer to 1 is better fit. Closer to 0.75, slightly worse. And then we're using the cutoff of 0.75. If you looked at the actual line, it looks like this. Okay. And before I move on, I want to say something about the phrase least squares regression line. The reason it's called least squares is what this line does is it minimizes the squares of the error. An error is how far above each point is from the line or how far below each point is from the line. So here, our line would have underpredicted this point. But here, our line would have overpredicted this point. So we would have a positive error for this one and a negative error for this one. We try to minimize that. But because some are positive and some are negative, if I just added just the errors up, then they can cancel out and you can do almost anything you wanted to. So what they do is they square the errors so that everything becomes positive, and then they minimize the squares of those errors. So that's why it's called the least squares regression line. It minimizes the squares of the errors, the squares of how much we're off. So we already said that the line fits the data well. And then it says, I shouldn't do that. Let me keep this down. What would the line predict the murder rate for a state to be if the Brady scorecard points of a state were at 0? What would the line predict the murder rate for a state to be if the Brady scorecard points were at 3? So 0 and 3. So we're saying if x is equal to 0, what happens? Or if x is equal to 3, what happens? So we plug in 0 into our linear equation, into our least squares regression line, and we get a y value of 4.65. So the line would predict that if the Brady scorecard points were at 0, the murder rate would be at 4.65. This is murders per like 100,000 people. So. And in the same way, if the Brady scorecard points were at 3, what would the line predict the murder rate to be? Well, we just type that in, 0.07 times 3 plus 4.65 becomes 4.85. 86, excuse me, I misspoke. 4.86. So the line would predict 4.86 to be the murder rate if the Brady scorecard points were at 3. Now remember, this line is doing a prediction. It's not going to be a perfect prediction every time because our points, as we saw, there's a bunch of points that were off the line. Okay, so it's doing a prediction, and you could give kind of a range of understandable numbers that it could be. But this is what we call a point estimate prediction. It gives us one value. Any questions about that? Just plugging in values into the line, into a word problem. Okay. Here's another example. This is on McDonald's restaurants and overall level of happiness in the country. Okay. So you can see where the data was collected from. We have 11 countries, and we're looking at how many McDonald's per million people are in the country, McDonald's restaurants per million people, and the overall level of happiness. Now, the overall level of happiness can be judged in numbers of a lot of different ways. We're going to use what's called the Cantrell ladder score. This is a well-known score about satisfaction of life outcomes or something like that. So it's this statistical measurement called the Cantrell ladder score, which in layman's terms gives me the overall level of happiness. Okay. If you did a scatter plot with these data, where X is the number of McDonald's restaurants per million people, and the Cantrell ladder score is the Y, you get a scatter plot like this. Does that look like there's going to be a strong linear relationship there? Yeah, no, that's not going to be a strong linear relationship. And so just by the visual, you can see that it's probably not going to be a strong linear relationship. But if you go ahead and do the calculations, you get a least squares regression line of y equals 0.01x plus 6.66. And an R value of 0.2163. So does this fit the data well? And the answer is, for our class purposes, no. It's under, we get an R value, which in absolute value is under 0.75. So I'll say that the line is a bad fit to the data. Bad fit. Now, in reality, if we had a line which is a bad fit, we probably wouldn't use it in reality. Okay? However, if there's a question on the test that still says, do a prediction of the Cantrell ladder score if a country had 19 McDonald's restaurants per million people, go ahead and still do the prediction. Okay, and move. Even if it's bad fit, whether it's a good fit, bad fit, still do the prediction. So in this case, we're essentially saying what happens if X is 19, X was the number of McDonald's restaurants per million people, and Y was this Cantrell ladder score, which tells you overall level of happiness. So we plug that in. And see what happens. It would predict the overall level of happiness as measured by the Cantrell ladder score to be 6.85. Any questions about that? Is that pretty straightforward? Hopefully. Again, it's like a word problem where the technology provides you the equation, okay? But we also have to know that this equation might not be as precise as the stuff we were dealing with last time. When this is making predictions, this is probably going to be not a very good prediction, right? Because this is a bad fit to our data. In our previous problem, the prediction was probably okay. In the problem before that, our prediction was probably a lot better. The higher that R value is, the closer it is to either 1 or -1, the better the predictions are going to be. Or likely to be. Oh, I did want to do this, but I won't go through this entire thing. But I did want to share this. Let's look at something that's close to example 1, where we take years as our X values, and then we'll take Y values, in this case, as abortions in the United States. That's a controversial topic, but we're not going to get into the morality of pro-life or pro-choice or anything like that, okay? So what we're going to do is we're just going to look at the numbers. Number of abortions in the U.S. from 2009 to 2018 is this in thousands. So when I say 789, that's 789,000. In 2015, it was 638,000. In 2018, it's 620,000. So these are in thousands. Now, the only thing I want to do is state that just like example 1, we could have created our scatter plot where the X values are the years and the Y values are abortions in the United States in thousands. Okay. However, a lot of times, instead of using the actual year, people will change this x-axis to be years since a certain year. Let me rephrase that. So instead of using 2008 as my starting value, I'm going to use 8 as my starting value. So 8 is going to represent the year 2008. 10 is going to represent the year 2010. 15 is going to represent the year 2015. And a lot of times that actually is nice because it gives us numerical values in front of the x and y-intercepts, which may be a little bit easier to deal with. Okay. So people will put an arbitrary year as the start. So in this case, it was years since 2000. So 2008 would be 8. Other times, people would use 2008 as year 0, and then 2009 is year 1, and 2010 is year 2, et cetera, et cetera, et cetera. You know what I mean? So if you wanted to adjust the years, and instead of starting at 2009, you started at year 0 as 2009, and year 1 is 2010, and so on and so forth. You could do that, just know that your line is going to look a little bit different. The difference in the line is actually not on the coefficient of x. Coefficient of x is going to be the same either way. Because if you increase by 1, in both cases, you're going down by 20.13. You know, the jump from 2008 to 2009 is the same jump from 0 to 1. Okay. But you'll see that the y-intercept is very different. Notice that the R value is exactly the same. R value is negative 0.9606 in this example. By the way, is that a good fit or a bad fit? That's a good fit, right? And absolute value, it's above 0.75. So drop off the negative, it's above 0.75. So in both cases, you get the same R value, you get the same coefficient of x in both cases, but your intercepts are different because you're using a different starting value for your x. In the first one, I used 80 as the starting value, so 2009 means 2009, x value. In the second one, x was years since 2000, so 9 as your x would be 2009. Pretty straightforward. So you can actually use either way and then predict in either way. Oh, that's what I was going to do. Sorry. Now, the last type of question, I would ask on a test or on a homework is just looking at various scatter plots. So this one is a scatter plot that represents marriages in Michigan in thousands. So for instance, in 2014, there was like 57.1 thousand marriages. In 2015, there was 58.8 thousand marriages in Michigan. This is that happened in that year. Notice that 2020 dropped off to 42.0. So way less than 2020. Why would that be? COVID, yeah, the COVID stuff. So COVID stuff really dropped off the number of marriages that happened that year. So anyways, interestingly enough, I don't know what it is now. I think the data set has more, it goes past 2022, but can't remember. But this is what it looks like. Now, if you were going to guess at the R value based on this scatter plot, would you guess that the R value is a positive number or a negative number? Negative. In general, the trend is going down as you move towards the right. So I would guess this. Now, there is a trend. So your R value is probably going to be an absolute value bigger than 0.75, but it's not going to be like 0.99, right? So if you had to guess at the R value, you might guess it to be negative 0.8, because it's negative direction, somewhere in there. On the test or on a homework, I'll give you a couple of options, and I'll say, is this R value more likely to be negative 0.99, negative 0.88, or negative 0.8, or negative 0.1? And out of those three options, it'd probably be negative 0.8. Makes sense? In this case, it happened to be exactly negative 0.7176. Now, obviously, there's no way visually that we're going to see the difference between a negative 0.7 and a negative 0.8, right? That's going to be tough to see visually. But we can see the difference between negative and positive, and the difference between something that's really, really close to negative 1 or really, really close to negative 0.75. Let's take a look at this one. Here's another scatter plot. Is the R value going to be positive or negative? Positive. General trends going up. And it's going to be pretty close to 1, right? Might not be exactly 1, but maybe it's 0.98. Maybe it's 0.97, I don't know. Something like that. And again, on the homework, you're going to give like 3 options, and they're all going to be quite different. How about this one?
Closer to 0.
Close to 0, right? That's it. That's all we're looking for. Close to 0. This one's close to 1. That one's close to like negative 0.75. This one's going to be really close to 0. And that one's going to be close to like, I don't know, negative 0.85 maybe. Something like that. It's not going to be exactly 1 because they're not on a perfectly straight line. But there is a definitive general pattern moving down. Negative 0.85, something like that. Now, I want to give, before we are done here, we only have a few minutes on this material. So before we're done with material, I want to give a few things about regression and this doing predictions to watch out for. One is the idea of extrapolation. When we do our predictions, we don't want to predict outside of known bounds. So, because for one reason, sometimes we get ridiculous answers. And for another reason, we don't know if this trend holds up or is going to hold up forever. Okay. When I say predicting outside of our known bounds, I mean plugging in X values that are like way big or way small compared to the other X values I have. So in a couple of these examples, we looked at trends from 2009 to 2018. If I'm trying to predict what's going to happen in the year 3000, that's probably going to be useless. Okay. Even 20 years from now, those predictions might be useless. Okay, if I try to predict in 2050, it might be pretty bad. So we don't want to do that extrapolation. Interpolation means that you're predicting inside of known bounds. That's a good thing to do. That's fine. And again, that's just because our model may break down when I'm outside of there. The other thing to watch out for when you're dealing with scatter plots and when you're dealing with these regression models is that oftentimes people will manipulate data and just use data that they like or ignore data that they don't like. So this was our scatter plot for McDonald's restaurants and the Cantrell ladder score. And obviously we got a bad fit scenario with this scenario. If I were somebody who was a very pro-McDonald's person and wanted to make it seem like more McDonald's restaurants are going to make people happier, well, what I could do is I could just ignore all of the data except for these 5 data points, right? And those 5 data points would make a pretty good straight line with a positive slope. You'd have an R value which would be positive and pretty close to 1. On the other hand, if I were a very anti-McDonald's person and I wanted it to make it seem like getting more McDonald's restaurants is going to make people less happy, well, there's a lot of other groups of data points I could have picked for that. I could have picked these data points here. Oops, I didn't circle that very good. Is my mouse? Let me go that again. Mouse. Not doing what I wanted to. Okay, so I can pick those data points there. And those data points are going to form a fairly straight line. The R value is going to be negative, something pretty close to 1. And so if you ignore the data points that you don't like and just look at the data points you do, you could also have done that with this group of points here, right? Those 4. Then you can come up with almost any conclusion that you want to, right? If you ignore a bunch of stuff that you don't like and just focus on the things that fit what you hope is going to happen, then you can come up with any model you want to. There's probably analogies to politics in there somewhere too, right? Ignoring data that you don't like, just watching data that you do like, or something like that. Okay. All right. So, any questions about section 2.4? This linear regression stuff? Pretty straightforward. Like I said, I'm not going to ask you to create these models with technology. I did provide a couple of videos, so in that video section, if you wanted to, check that out. How to create a regression model with your TI form calculator, or how to create a regression model with Excel in more depth than I just did. You can. But that's it for section 2.4. So that means we're done with material on unit 1. Okay. Obviously, I was hoping to have all of this done last class period, but didn't work out because I had this weird delay in schools, so I had to take my kid to school. So I only got about an hour last class period instead of the usual almost 2.5 hours. But let me ask you this. Any questions you have for me over any of the homework problems, anything on the test, things like that? Push pause.